Well, it's really good to be here, and I'm sorry I was absent the past 2 days. In the midst of all this, I'm actually going to be moving to the University of Kansas, and so literally as we speak, they are like loading my apartment into a container. I told my wife this morning what we should do is we should just gamble and like post and say, look, for 3,000 euros, you can buy an apartment. It'll be all boxed. It'll be a surprise what you find, and we can just, get on the plane and start anew. But she was not into that as much. Earlier we talked a lot, Ralph was talking a lot about, we kind of made these references to the environment. And so with this talk, we'll kind of work on this aspect of the environment questions and risk-reward relationships. So I thought I would motivate this, at least give you a start, and I'll introduce you. That's James Stockless, the guy right there with the hat. Clearly, he's pretty happy, right? His family is celebrating. The story is he's a judge in Pennsylvania on a fishing trip to Florida, went into a local convenience store, bought a Powerball ticket, right? And a few weeks later, found out he won. So he's pretty excited. His family is pretty excited. Now, it's not as clear, but now that's his brother. His brother's not in the picture earlier, but actually his brother was also on the fishing trip. On the same day, at the same store, also bought a Powerball ticket. But Bob won $7 as opposed to $291 million. Now, let me just point out a couple things, right? It's also really hard to find out what Bob does. If you go read the articles, they tell you that James is a judge, but Bob we don't know about. I have to look at the picture, and if you can see, James is much happier. Bob is a little bit more straight-faced. It's a little, and also look, they added 2 zeros. Now, what this picture illustrates, right, is at least gets you to think about, well, one, the strange happenings with chance and luck, but we also probably have an inference, right, that both of them winning's really unlikely, but James, the probability of James winning that is much less likely than Bob, okay? And Bob probably had a little better chances, and James also had a better chance to earn $7, or actually most of them probably to earn nothing, right? And that is illustrating a relationship that actually Ralph and I kind of stumbled upon as we were kind of talking about these environments that we were thinking about. And this is what we started to think about, this risk-reward relationship. And so what I'll do today is to walk you through where we've kind of gone over now, I guess, the 10 years of thinking about this question. Wow, risk-reward relationships, that seems a very prevalent ecological structure that we run across in the world. What are the consequences of that structure? And how might people use that in their everyday decision making? And one of the ways we've thought about this is in terms of a heuristic, what we call the risk-reward heuristic. And I'll frame that in with a football bet, okay? But I'm not going to talk about whatever you guys call football. The real thing that I'm concerned about is the Chicago Bears and the Green Bay Packers. When they play in the first week of football, there's no, whatever. This is real football. And now, now this is big. If you know, these two teams are on the gridiron, right? This is like classic American football. Would you pay $2 for the chance of winning $10 if the Chicago Bears beat the Green Bay Packers in the first week of football season this year? Okay, so think about that bet. Now you could maybe think about, well, maybe I would or maybe I wouldn't. But I would also suggest that this might actually give you a hint, right? That this bet is a way of conveying a probability or chances of something happening. And maybe because you guys look at this other type of football more often, you don't know very much information, so you might use this information contained in this bet as an estimate for your probabilities, right? So you don't look for other information, you don't consult your friend, you might not have to look at your phone, but you can look at and say, okay, look at that bet, let me start there. And that is one way, that's what we call the risk-reward heuristic. And I can frame it in a precise way for gambles that offer a single payoff G and otherwise nothing. Estimate the unknown probability of winning from the ratio of the cost of playing the gamble to the total amount of possible winnings, right? So that's a reasonable, seems like a reasonable starting point for inferring the probability of that event. Okay? And we call that the risk-reward heuristic. What I want to talk about today is, well, what do we know if people use that heuristic? That'll be one question we can ask. But there's also, you can start to think about it, and now I want to take a step back and as a point in terms of the Summer Institute, that you can start to think about the challenges that any heuristic or any adaptive strategy or process faces, right? That actually has to live up to kind of, so that you could say, okay, look, this seems like a reasonable thing that people might do, and it's a reasonable way for me to claim that it's an adaptive strategy. So one of them would be what I call the environmental challenges, right? One of them, Ralph kind of hinted at this. One can only expect cognition to adapt to the environment or the environmental structure if the environmental structure is frequent and recurrent, right? So it has to be repeating and reliable in order for human cognition and the mind to adapt to it, right? In order for it to come out. That's one challenge. Also, we should be able to predict a priori, this is more of the challenge for the theoretician or the psychologist, right, or the adaptive theorist, to predict a priori when an environment will have a structure and when it won't, right? We should be able, I shouldn't just have to look and say, well, wait, let me go look at this environment and see, and then I can tell you what behavior is going to be like. I'd like to know if that structure is going to be there, and then I can kind of predict behavior. That's one side of sign and blaze, right? The other side, right, are the cognitive challenges that if you want an adaptive strategy that it has to meet, right? Or there's many of these, but one of them in terms of the risk-reward relationship is the mind has to be sensitive to the environmental structure, right? Not only does it have to be in the environment, but in a way the mind has to be able to take that up explicitly or implicitly, right? And be aware of that. You have to be able to represent that structure to use it. And moreover, if the structure varies across environments, right, so if it changes, if it's not just ever present across every environment, and if we claim it's an adaptive, then people or the mind should adapt their use of that structure if it's an adaptive strategy. Yeah?
Would you define frequent and recurrent? Like, for instance, there could be disasters that are pretty,
rare, right? So
how do people adapt to that?
well, so, or not, or maybe more like if that thing, it's not so much the actual disaster, right? But if the thing is a rare event is a frequent, that's actually maybe what makes it hard to handle those rare events, right? If they're not very frequent, and you won't adapt to them, right? It comes out of evolutionary aspects, right? So if you want to start to evolve, you have to be able to rely on that so that you can start to use that situation. So it has to be frequent. Happening enough times that you'd run across it. So if you think about an evolutionary process, that it would select on it. And it has to be recurrent, right? It has to keep happening enough that I could actually start to use it and I can actually see it shaping. So if you think about an evolutionary process. Does that help?
The dinosaur, like the meter is like too
They weren't adapted, right? They didn't have umbrellas or shields or something, right? That would be one way to think about it. Okay? It's a good question. So, those are the challenges by which we've started to think about with Ralph and with Christina and others. Hey, can I test out if people use this risk-reward heuristic and kind of how far can I push it as an adaptive strategy? And so what I'll walk you through today is the way we've challenged the risk-reward heuristic to see how far we can push it and see if it holds up. So I'll talk about the environmental challenges we've done, which is the risk-reward structure a frequent and recurrent structure? What are some of the basic ecological properties that give the risk-reward structure? So that'll be the first part. The second part will be the cognitive challenges, right? Just some of them, which is, hey, is the mind sensitive to this risk-reward structure? Can it pick it up, right? And do people harness the risk-reward structure flexibly? Finally, I'll try to also, at the same time while we're doing these, we've been starting to kind of look and ask, okay, what are some applications of the risk-reward heuristic, or at least the mind using the risk-reward structure? And I'll talk about learning from others, identifying good options, and identifying bad options beyond just estimating probabilities. So is the risk-reward structure frequent and recurrent? Now, one of the papers that we put out was the paper Ralph and I first wrote on this idea. This was our first attempt to kind of get a grasp on what's going on. And so this actually is almost the first thing I did when we started talking about it, is actually we were coming back from the casino at Basel. We had done a group trip, and so roulette was on my mind. And I said, well, what's interesting, if you take roulette and you look at the payoffs, and then you calculate all the possible payoffs you could get at a roulette table, and then you plot the probability of a win, you get this nice power law function or hyperbolic function, right? Shaped like this, right? Where the payoffs, the really low payoff, is more likely to happen than the high probability, right? So you get that shape, right? And for me, that was interesting because, well, that's a really distinct shape. Now, does that occur in other places? And the answer is yes. And so then what Ralph and I were struggling with is like, man, okay, how do we figure this out? So we went around and we were just sampling and say, okay, what about this environment? And so one place was I was able to obtain data from another set of French researchers who had gotten all the bets placed at a horse track for 10 years. And so what I plotted was the payouts relative to the 1 pound bet, right? And the probability or the relative frequency of that horse winning, who was given those odds. Now, what I've done, notice I've plotted, this is roulette, I plotted this in a log-log space, so that's the same relationship, but now it's linear, and that's what should happen. And now you can see that that same relationship happens for horse races. This happens up here because there's actually a fair number of below one odds given at horse tracks for some, we'll come back to, right? So that happens up there, but you can see a linear relationship. You get the same thing with the life insurance. And then we were saying, okay, yeah, that's great, but we knew that if we go and talk about this, right, people will say, well, yeah, but these are kind of man-made. People really sat down and maybe even constructed these gambles. Can we see this relationship in other places? And so this is where different places we started to. One of them, which has always been a fun story and earned me lots of beer, is that I talked to my brother, who at the time was doing artificial insemination of dairy cows. In the Midwest, and he said, when I go and I have to basically sell the semen to the farmers, they have a catalog, and they're basically told to say, hey, look, here is the payoff that will come to your farm in terms of lifetime net merit if the cow is successfully inseminated. And here, by the way, is the sire conception rate, which is the probability of a successful insemination of the cow with the semen. And you get a negative relationship between those two properties. Now, you can also, we said, well, there's other places, like, for example, a gamble that many of us face more is where we submit our papers, right? And so you can look at the journal acceptance rate and the impact factor, you get a negative relationship. You can also look at, for example, in ultimatum games, in bargaining, right? The amount kept and the probability of the person accepting it, and you get a negative relationship. Now, this isn't exactly a power law or a hyperbolic function, but you get a negative risk-reward relationship. Okay? So this thing, I would claim, is at least a start point to say, hey, this is seems like a frequent and recurrent relationship that we probably run across in the world, right? Not necessarily in the laboratory. Now, so that would be at least a survey inductive approach to say, okay, we can start to see this. Now, you can also start to ask, what are some basic properties? And I'm going to flip between these two questions. But for this, it's useful to say, okay, now we can also use this analysis to start to kind of get a hint as our first intuition of why that structure appears, right? And many of you probably have an intuition, right? And to kind of foster that, I'll go back to this bet about real football, where we have the Bears and the Packers. And we can say, okay, when is this bet fair, right? This bet is fair when the expected gain, I'm going to call that G prime, so the G prime plus C, so when you make a bet, you hope that whatever you paid into it will also come back to you. When it offsets the expected losses, so P times G, 1 minus P, And what probability P makes this bet fair is when P is the ratio of the cost over the total gain, right? C plus G prime, okay? Now, so now that gives you your first hint, right? Now you can say, okay, is that coming out? And in fact, if I plot that value in these graphs, particularly at the top where I have actual payoff values, right? Then you're quite close, right? You're within plus or minus 0.02 for roulette. Here it looks like it's far away, but it's actually on a log scale, so you're within like 0.02 probability, right? If you just looked at the life insurance payout and then you estimated the probability, you would be pretty close. Now you could say, well, what about down here, right? And that's just partly the question I had kind of going forward is like, okay, so this would say part of the structure, right, is how those gambles are constructed. The forces of the marketplace, right? You're not going to buy terrible gambles, right? And companies don't want to sell terrible gambles, and they also don't want to sell really awesome gambles often, right? And so the forces of the marketplace pushes those gambles to this frontier, this Pareto frontier, right? So it's going to push that way. So that's why it becomes a reliable structure, at least for man-made structures, right? And you could make some claims that that's probably operating down here at least. We can come back to the ultimatum game at some point, but there's maybe different things going on with the ultimatum game.
Sorry.
Yep. Go for it.
You mentioned that companies do not want to sell terrible gambles, but to the extent that people are blind to the...
Okay, yeah, you're right. Well, there's two parts. Companies don't want to sell really awesome gambles, right? Although we'll talk about that question later at the end of the, but why they don't want to sell terrible gambles, right? For example, when I talked to the companies that were selling the semen, right? If you actually look, you can actually get all the semen they could sell. They have a much larger sample that they could sell, but they don't have very much page length, and so they don't even bother to put the terrible semen on the pages of the catalog, right? Because it takes up space. So in a way, they actually are saying, look, we only have so much time and space, and we can only sell this to the farmers, so they actually trim out the bad options automatically. Same thing with journals, right? You could say, well, look, there's some journals that are, have a low acceptance rate and also a low impact factor, right? And maybe those are sometimes are the newer journals, right? Or some weird things are going on there. So I would say that's not quite right? They actually they only have so much space. So there is some trimming of dominated options that also happen on the side of the company. Other questions?
But there's really more human selection in some sense, right? So
yeah, so I think for a lot of this, at least in the marketplace, right, that we run across, that there is some selection process. Now that's on the side of the seller, right, and the buyer, but that also means that it's an ecological structure that we all can kind of learn to exploit and to use, right, if we have to estimate the probabilities, right? And that would be, at least in my mind, consistent with a heuristic idea, right? Ignore information, I'm going to make a bet about the structure of the environment.
but that's evolution very recent.
What's that?
The evolution are all very recent.
Perfect. All right, so now we had that actual question, right? So this is a very recent thing. Would this be something that we adapt to, right? And kind of make a larger claim? So I'm going to have to take you a step back. And this actually is where we started to talk with Larissa Conrad, who's not in our, she's an adjunct researcher now. She's a behavioral ecologist. And she basically had almost the exact same question, right? And she said, let me tell you about the ideal free distribution. Let me tell you about that, and I'll tell you where I'm going with it in a second. So let me give you an intuition. So think back when you came here, right? Most of you took the plane, right? Now, if you're like me, you have this problem, right? You have to pick the security line you want to go through, right? Because the plane's going to leave, maybe, and you have to figure out, do I want to stand in the longer line or the shorter line, or how do I figure this out, right? Now, behavioral ecologists have studied this question in a different way, and it's called the ideal free distribution. And if you watch people, you can also do this at the grocery store, right? Which cashier line are you going to go in? There's an interesting dynamic that happens, right? As a passenger, you're going to want to pass through the security line as quickly as possible. Most sane people have that, right? with multiple lines, you pick the line that you think is moving fastest, right? So I sometimes think, okay, wait, that longer line, but maybe it's actually, it seems like it's that person up there, they're going a little quicker than this shorter line, right? So is everyone else, right? So it seems reasonable that everyone else is thinking all this. So this is actually going to produce a dynamic equilibrium where the average wait time, right, in the end, it will be similar for everyone at the end of the lines, right? So if we're all doing this, it'll form an equilibrium where even if you go to that short line and that person is going really slow, your wait time probably will be about the same as the person that went to the longer line that had a person that was processing it quicker. And that is forms what's called the ideal free distribution. We can state that more formally. The number of competitors, I'm going to change from, now think about, now you're a competitor. This is in biology, so they talk about competitors. In a number of competitors n in a patch y is going to be proportional to the amount of resources. Okay? And that's called the ideal free distribution. And that's a property that behavioral ecologists have studied. And in fact, it's great reading, actually. It's a lot of fun. You can find out, like they talk about this biologist that went to a pond outside of Cambridge and then threw breadcrumbs right into the pond and saw how many ducks went into the pond where he threw a lot of them and at the same time was throwing fewer breadcrumbs. So mallard ducks distribute themselves consistent with its ideal free distribution. Northern pike fish, dung flies, undergraduates. My wife didn't think I should do dung flies and undergraduates next to each other. Fishing vessels, job applicants, all these people and all these seem to conform to this property if you look at it at the aggregate level, right? So that's actually saying, look, there's how people distribute and how competitors distribute seems to conform in the world like this. Okay? Now, what does this have to do with the risk-reward relationship? Now, Larissa came up with this example, and I like it enough that I borrow it all the time now. Let's talk about cupcakes, right? So now I have two patches, right? Both of them have the same number of resources, but the size of the cupcakes are different, right? Now, who are your competitors? They're the toddlers, right? So where's the first toddler going to go? They're going to go to the patch with the big cupcakes, right? The second toddler comes along and says, well, wait a minute, I'm going to go over here. I can get my smaller cupcakes. The next toddler is going to go to the bigger one, and you can now play this equilibrium out where you could see how this would go, right? Now you can imagine also the cupcakes refresh each other, etc. Now, that's an ideal free distribution. Now, I've actually changed, I'm going to change it slightly. I'm going to change it from the amount of resources, and I'm going to say, well, the amount of resources is just the number of resources times the size of that resource, right? And so that's just a rephrasing of the ideal free distribution. And now I'm going to say, well, look, what about these new toddlers that come along? What's the probability of their success, right? And well, it seems intuition would tell you, right, the probability of successfully getting that cupcake is going to be directly proportional to the number of resources in that patch and inversely to the number of competitors, right? So now if we substitute, right, and we just cross off, you can see with the ideal free distribution, what I've just done is showed you that actually with an ideal free distribution, if competitors distribute themselves in an ideal manner, right, that will imply at the equilibrium there will be a risk-reward relationship. The probability will be inversely related to the size. And this at least goes to one start to answer to your question, right, is to say this actually suggests not just man-made markets, but any time there's competition over limited resources is a sufficient condition to create the risk-reward relationship, which would then say that's maybe even a stronger claim about the frequency and recurrence of that property. So long as we have this competition over limited resources, which seems like a sufficient condition that often happens, we should, in general, often see a risk-reward relationship. Now we can take, what we've done is taken that work further, right? Now there's assumptions that come along, and actually those assumptions start to kind of illustrate when and how that risk-reward relationship is going to change. And it's going to change it in interesting ways. We have a big long table. There is no way you're processing that right now. You should be just, like there's 7 things. Okay, good. There's 7 things. But I'm going to pull out 3, right? So one of them is, let me show you, think about this. Heterogeneity and resource sizes, right? So I showed you cupcakes, and they have the same number, there's the same size in cupcakes, right, in each patch. And you can say, well, is that, how often does that happen? And what would be the impact on the risk-reward relationship? So what we can show, right, is as the heterogeneity or the variability in the size within the patch comes to match the variability between the patches here, then you're going to get no risk-reward relationship, right, due to the ideal free distribution. Okay? So that's one intuition. So that's at least a prediction we can say where we would see the risk-reward structure and where we wouldn't. We've also done other things, right? You can, this one takes a little bit more work, so you maybe just have to trust me to give you a little intuition. We can say, okay, look, what about the number of competitors and resources in a landscape, right? So here's the plot where when there's a lot of competitors and a lot of resources across the landscape of all the patches, there you have a very strong risk-reward relationship. When the landscape becomes sparse, for example, this is the extreme condition, when there aren't very many competitors and there aren't very many resources, then that risk-reward relationship is going to start to break down. But it breaks down in a very interesting way, right? Is that you can see here, right? There's not very much variability about the probability of success on the big high payoffs. But at the lower ones, you get a much larger range of possible payoffs or probabilities, right? So that's a particular interesting prediction we can start to ask, does that appear and how do people use that? By the way, the term ideal, right, I'm kind of sinning a little bit in this Summer Institute, right? Ideal, right, is they're making an assumption about the competitors, right? When we say ideal, that means that basically the competitors are essentially homo economicus, right? They can look at the patch and they can perfectly detect, right, the consumption rate of that patch. That's the assumption in the model and the theory, right? And then you can say, well, what if we break that down, right? So that they're not very good at detecting those differences. And when it breaks down, it's hard to see is, Christina is always telling you about this, is that it becomes shallower, and it also becomes related to the variability in the number of resources, in that very much like that landscape saturation problem, right? We get, again, where at the low resource sizes or low rewards, you get a much larger range of the possible probabilities, right? So in other words, in this case, with non-ideal competitors, more realistic competitors, and variability in the number of resources between patches, the big payoff is going to be a reliable cue to the probability, but the low payoff is going to be less so, right? Much less so. Now you can ask, are there indications of this, right? So we talked about the market, right? But you could, I don't know, you could say, well, maybe that actually gives some also aspect to so here's the submission to psychology journals. You get a much larger range at the bottom versus the high. And that didn't come in as well. Now, this is a study that we ran where what we do is we give people a bet that they have to pay $2 to play. And then between subjects, we manipulate the size of the possible payoff. And then we ask them, essentially, what probability do you think you could win with, right? Either before or after the choice. This is the red line. This is the risk-reward heuristic. Now you can see A, shallower, which is consistent with the ecological structure that the proof I just showed you, this relationship to the ideal for distribution, and something that I always was troubled by, but I never understood, but curiously corresponds with the ideal free distribution prediction, is that there's much more variability in the probabilities people estimate for the very low payoffs. as opposed to the very high payoffs, right? So this would say there might be at least, this is, there's some correlation or correspondence between what we predict from the theory and in terms of what we see people's estimates are in terms of what they think would go with, what probability goes with what payoff. So let me recap 1 second. So that's some environmental challenges. So I hope I kind of conveyed to you that, look, it seems like we can make a strong claim that the risk-reward relationship is a frequent and recurrent relationship. And I hope to kind of convey some of the basic ecological properties that give rise to the risk-reward structure. Certainly the operation of markets is one key component. But a more general version is the competition over limited resources. There are also many other things that can give rise to risk-reward structure, but at least those are stuff that we can start to say, hey, I can now start to predict when I'm going to see a risk-reward relationship and when I might not see it. Yep.
So I'm confused about one thing that you showed when you first introduced the cupcake example. You had this relationships between the number of competitors that will be proportional to the amount of the number of resources times the size of the resources.
Yeah.
In which case, it seems to imply that it's a divisible resource. Whereas you showed that the risk-reward is an indivisible resource, and so is there a problem with that?
So that's where I have to be cautious in terms of the empirical data, right? I mean, the way this is talking about is in terms of a finite resource, but that could have different sizes. Is there a problem if the particular resource, if I'm understanding your question, if it's actually divisible and maybe it could get shared among competitors?
Yeah, because I just thought maybe the first equation sort of implies that it can, because is it obvious?
Yeah. So, and then here it's not. And so that's also where I have to say, so that's where, right? So this is talking about different resources, right? I'm assuming in here that they're not divisible, right? That it's a function, right? So it's not the exact same. The marketplace is with the divisible resources, but this is actually where they're clumped together. It's a good point. And I haven't worked through how that would, if we go to a place where these cupcakes are divisible, right? And what that implications are. I can't think on my feet right now on how that would operate, but it's an excellent point.
And I just have one super quick other question. So the last graph you showed, where you showed that the probability, the variabilities were quite low for the right side of the graph, but quite high on the left side of the graph. How do you distinguish that from the possibility that it's just an underestimation of probabilities across the scale and you just have a forward effect?
Okay, so we've compared the models, particularly with that. So so the range, how do I do the floor effect? Yeah, okay. So they're compressed, right?
So they can't get any lower.
They can't get any lower. You're right. This could also be due to that, but there should also be some spillover, right? So into the variance, right? It could be that. I can't necessarily get rid of that aspect, but I can also say a continuous structure. But you're right. There is one alternative explanation that, to the degree we can model it and account for the variability. So the way I handle it right now is we have a model that has the stochasticity built in. So not only do they make the risk-reward, but they're noisy estimators, right? And I can compare the model where it's just noise and a model where you have the risk-reward aspect with this built in. And the model with the risk-reward aspect built in does better than a model that just has the stochasticity built in. Yeah? Good question.
So in disentangling the market effects, so you mentioned this could be that people are already have been educated about markets, and so then they're kind of playing the role of equilibrating the local area. Have you done any research on non-Western societies or anyone that may not have this?
That's a good question. We haven't. The furthest east we've gone is Germany. But that would be a question, an excellent question that we haven't done. That would be really cool to kind of ask how that extends to different places that have different market structures or don't have the free market structure, right? A prediction might be that that risk-reward relationship would break down, especially in context and questions about the market type of gambles. Yeah. Yep.
Follow up on Doug's question. So if you assume some like specific function that just for like low reward magnitudes is actually statistically magnified, then the noise would also be higher.
What I hid the modeling in here, but so what we have is a model that has this component in there, right? So it has a logarithm, so that actually is a key, one other aspect that's going on in here. In fact, that's essentially how we model the non-ideal observers, right? Is we actually add them in so that they don't they have diminishing sensitivity to the rates, right? And then that function, like for example, if you do like an exponential function, you get like a 0.5. So they're definitely diminished, right, in terms of their detecting, right? The model still has that risk-reward relationship, but it's in there, right? Good questions. Yeah, so what we've done is do these model comparisons to at least quantify and say, look, at this point, that's the evidence is consistent with that. Okay. So with those, right, so that's what we've thrown at it in terms of environmental challenges. Cognitive challenges. Is the mind sensitive to risk-reward, the risk-reward structure? And this is basically day one when Christina came in to do her PhD. That was basically the question we asked her. And so what we, to kind of figure out, how can we look at this question? So what we did was we devised a way to kind of see if people in a laboratory sense could pick up this risk-reward structure. And so what we came up with, there's several different iterations of this type of study. All generally point the same way. What we devised was, in this case, we have a task where we have a couple people come in and do 100 to 150 gambles. Okay? And we just show them a gamble, and we ask them to state their selling price. Now we do it in a BDM pricing way so that we can pay them off and they're incentivized to give their honest, as best they can, their best selling price. And we just show them these gambles one by one over 100 times and ask them just a standard decision-making experiment that you might run. What we do, though, is behind the scenes is people are assigned to one of three conditions. Now, we don't necessarily do this, but we do a linear negative relationship. It's just easier to kind of work with and think about. Where we have a negative condition, and that's these gray dots, right? We have a positive condition, and then some people are in the uncorrelated condition, which, by the way, 99.9% of all laboratory experiments look like this that have been run, right? And so we were curious, do people pick up this risk-reward structure? We don't tell them anything. We just say, just price the gambles. And then after they finish that, we ask them some questions. One, in a counterbalanced way, or actually in a particular, so one of them is, the question is, did they learn this relationship? So then we show them in different ways, how likely do you think this reward is, right? So 347 $, we use $, so that we try to minimize the people coming in with their own expectations about currencies as much as we can. And then we ask them to state their probability. And what we show is that, look, when you come in and you're exposed to this negative risk-reward relationship, people pick it up. And when you're in a positive, like the fairyland where everything's gumdrops, right? You get a positive relationship. And here's the uncorrelated condition, right? So that says that if you do 100 to 150 gambles, you can pick that up. You see the structure. Now, the other question we asked, and we actually asked this first, before we asked them to estimate the probabilities, was, hey, would they use this when they have to make choices? So do people harness the risk-reward structure flexibly? Right? So if they're in a context where there's a positive or an uncorrelated, right, do they use that in making their decisions? So we ask them questions like this. Do you want this gamble or this gamble with an unknown probability, right? So do you want 122 $, with a 100% chance, or here, right? And here's the results that we got, which we were excited about, right? Is here. We can see, now look at the positive condition. People in the positive condition, exposed to it, picked it up, and made their decisions as if, and using, consistent with a risk-reward type of prediction, right? Inferred the probability would be positive. You can see the negative, it's not as strong in this experiment. In fact, it's almost very similar to the uncorrelated. In fact, often when we run the uncorrelated condition, it tends to be biased towards the negative. In fact, this study, this one, we often find the positive is more like less negative, right? So they pick up the negative is a really strong prior to get over, but you get that relationship in, okay? So that's also showing you, here's a context type of effect, right? People's preferences change based off of the environment that they were exposed to, right? And that's something that isn't in the current kind of thinking about how people make decisions under uncertainty, how the context of the gambles that they've been exposed to impact the choices. So that gives you, at least I would argue, here is some ideas of ways we've thought to, okay, how can we challenge this and push the risk-reward heuristic to ask, does it seem like a plausible, does it live up to, does the human mind have the conditions you need to do that? I'm going to go over a little over time for questions. Yeah, okay. Because I want to actually highlight 3 things and I'll come to a conclusion, okay? So we had some questions and I'll go through that. Applications of the risk-reward heuristic. So now what we started to do is say, okay, now are there some places that we can see evidence of people using the risk-reward heuristic? The first one is it's a way to learn from others, and this is work Christine next to Christina and I have been doing. And it comes with this idea that, you know, if I bet you money, it's a little bit like the risk-reward heuristic, right? The probabilities say that, right? But we've been asking to what degree can we pick that up if people, do you learn from others, right? Do you update your own beliefs based off of the bets that people are offering you? So, and we wanted to see if we can pick this up in just everyday bets that people are offered. Now this is an everyday / not so everyday bet, but so imagine this one. Each day on your way to work, you walk past a coffee shop. The shop has recently started a new advertising campaign. They bake fresh tea cakes regularly throughout the day and have a clock outside that shows how long it has been since the tea cakes were taken out of the oven. You are interested in buying a tea cake as soon as it is removed from the oven and wonder how often batches of tea cakes are baked. Today the clock shows that it has been 34 minutes since the last batch of tea cakes was removed from the oven. So many of you might, this is a question that Griffiths and Tenenbaum have examined in terms of if people have priors and represent the priors, right? So do you have a prior belief about the tea cakes? We're going to adopt that, and what we asked was, we had one set of participants that got this condition. So after they thought about that, we should say, suppose you're being accompanied by a friend on your way to work. At the coffee shop, your friend makes the following claim. I think the probability that the next batch will take more than another 55 minutes is about 5%, right? So this is a straight forecast condition. This is equivalent to you getting the weather forecast, right? And you can say, well, what's the probability of rain here? What's the probability of it being done? Now we can have the corresponding condition in the bets, right? For the price of one, we did this with an online UK sample, graded GBP pounds, he will pay you 20 pounds if the next batch will take more than 55 minutes. And the question we had was, to what degree do people update their beliefs in a similar way given the information is basically conveyed in the same way, or same information is conveyed this way? Now I'm showing you this because this is the study that was like, okay, well that's really cool. We did this with the same subject, got all different scenarios, and the prediction wasn't a probability estimate. It was just to say, how much longer do you think this thing is going to take, right? So tea cakes or trains, toxins, etc. And now I've ordered the scale in terms of high, medium, low, so the delay amount that people were betting on. And the interesting thing for us, right, here's the forecast, and here's the bet condition, right? In general, at least this is evidence that is suggesting in these other formats, people are taking the bets not just as stimuli, right, that you could infer their preferences and beliefs from, but as ways to update their beliefs based off of, right? They're leaking information, just like the risk-reward heuristic suggests. And in fact, there was kind of a Bayesian type of question earlier. We can kind of couch the Bayesian, this risk-reward heuristic in terms of, we've couched it in terms of informing the prior, right? So informing the likelihood of the data coming in. So in a Bayesian type of way, and we can talk about later what that happens. But what happens when we model that is it basically says people treat bets just like forecasts, but they're noisier, right? They are a little bit like more uncertain about the information in the bet, and assume the bet is kind of biased. So the person that's offering the bet is going to be trying to make money, and their beliefs look like that. Okay, now that's one application. You can that the bets start to leak information. Another one is you can start to use the risk-reward heuristic to kind of identify good options, right? So this is a paper that came across my desk last year. It's an archive paper. Basically, these guys are now in industry, data scientists. They've moved on, but it's an archive paper. They essentially did almost the exact same analysis I did, but they did it with soccer bets. Right, and they looked over 10 years, and they looked at the bets that were offered by bookies for soccer games, that other football game, and you have the probability in terms of 1 over the odds, and the probability of that event occurring, and they got this relationship, right? Now this is in terms of probability, in terms of the odds, and the probability of being correct. And say, well, that's really interesting. It is over all of the odds, the bets being offered in soccer for 10 years. But they noticed something when they looked at that. They noticed that, when we look at particular bets, some bets stand out. And particularly, there were some bets that deviated significantly from that risk-reward relationship. And what they said was, well, actually, that seems interesting. Could we exploit that? They seem to systematically happen. And what they did then was they ran a number of simulations, but I'll show you this. They put the money down on it. Right? And they said, okay, what they did was developed an algorithm that basically said, look, any time a bookie's bets differed by like 5% from the average from everyone else's, let's bet on that game. And they put $50 down, right? They were able to do that and earn a profit of nearly $1,000 with a return of 8.5%. They were able to do that for 265 bets until the betting websites shut them down. And do a pretty good accuracy. So what they were doing was they used the risk-reward relationship, and this is what you should do probably. Like you should look for those really interesting cases that stand out and bet on them, right? And be them surprising or whatever. But actually, and then you could ask one question: is like, why are they doing that? And basically, at least according to the paper, right, and it seems plausible, bookies try to sometimes get you to come over to them and leave the other bookie, right? So how do you do that? You get someone you give them a weird, attractive gamble, and you get them to come over, right? And so what their system was doing was essentially finding those times that bookies were doing that and trying to exploit that. And now so you can identify good options, but I would say there's also some ideas of people using the risk-reward heuristic to identify bad options. And this actually comes from a talk we were all attending at Spudum. Ralph and Christina really kind of stumbled upon this. This was Al Roth was giving a talk about repugnance, right? That there are some things that we just think shouldn't be sold. And the idea here is about clinical trials. That, if we pay people for playing a clinical trial, some people will say, no, like that shouldn't be happening. I find that repugnant. That type of transaction should not happen, right? So what they did was they ran a study where they gave online participants a scenario and put them in the form of an IRB board, where it was about an Ebola virus, and now they're going to enlist 100 female participants to see if this Ebola vaccination would work. And each of the 100 participants were injected with the vaccine and then monitored in weekly intervals for 2 months. The key component was the institute will compensate each woman who participates with either 50 pounds, 1,000, 10,000 for the risk that she takes and the time commitment required to participate in the study. It takes about 40 hours, right? And we went, and actually Lazare's in here as well, we went and replicated that study. There's a bunch of data here. They asked him a bunch of questions. We replicated exactly how they did it. And I want to highlight two things. Well, there's a few things. The first process. One, and this is following the Amble paper, they found that there's basically two types of people, trusters and doubters. Basically, that essentially say, well, look, the payoff doesn't matter or the payoff does matter. And the doubters are in the blue. And what you can see is that first, let me look at the IRB approval, which we can start to see as a proxy for repugnance. That if you get a big enough payoff, there's a drop in how well you're going to think that the IRB should approve it, right? And that generally reflects lots of different things. And one of the reasons the Amble paper said was, well, that's because it seems it's coercive, right? The big payoff seems coercive. And the insight that we had was to think about, well, actually there's another thing going on, which is the payoff could be communicating the risk, the side effects. And so when we replicated that, we also asked them to rate the probability or the side effects per 100 participants. If there would be any side effects, mild side effects, or severe. And what you can see is in any, those doubters had a significant uptick in terms of how many side effects they thought would happen for any of the side effects. Now notice for severe, you can see it's mostly carried by mild, right? Moreover, what we can then do in a regression model then is to say, hey, in fact, it's not just voluntariness that explains the repugnance of these doubters, but also their inferred side effects. Okay, so which is interesting. Also, if you read the Amble paper, they basically tell you there's nothing about the side effects. It's all about the coerciveness. And this would be an indication, right, of a risk-reward kind of identifying what I'd say bad options, right, and saying, look, that's repugnant. And one of the reasons, at least in this case, people rate it as repugnant or something that shouldn't happen is not only just the coerciveness, but as a cue for something bad happening. So let me, I'll summarize and then conclude and give you guys some questions. How do the risk-reward heuristics stack up to the environmental challenges? I hope I showed you that it's a frequent and recurrent regularity that should allow the human mind to adapt to it. We showed that competition among limited resources is a sufficient set of ecological conditions to generate a risk-reward structure. So that's on the environmental side. And we showed you, in terms of the cognitive challenges, that people learn the risk-reward structure even if we don't draw their attention to it. And they exploit it in a way, they exploit it and making decisions under uncertainty, and moreover, flexibly adapt to it, right? So if they're in a positive or uncorrelated, they pick that up. So let me give you two concluding thoughts to kind of think about this and put it in a bigger perspective as you're thinking about the Summer Institute and the ideas that are being put out. I want to argue that we actually, this is a principle of bounded rationality, but I think this what it highlights what I'll borrow another term, boost. I think we actually need to boost the principle of bounded rationality. So this is out of the annual review paper by Simon, which has the scissors and other questions. Adaptive theories of cognition often take the approach that one, quote, must both construct a theory of the system's processes and describe the environments to which it's adapting. What I hope to have shown you is actually that term describe now kind of sticks in my craw, right? I don't think that's a very good approach, right? We should have a theory of the environment that is adapting to it. Why do we want that? Because I want to be able to predict, right, boundedly rational behavior. And in order to predict that, I want to predict what properties in the cognition arise, and also predict what environments that would happen. And only then, once I have an understanding of that structure and when it's going to occur, will I be able to be really predicting behavior from a system of bounded rationality. I want to also at least part with you, right? Ralph was talking about the eco-probable, and that actually brings me to this idea that Laplace once said that gets quoted once in a while. And that's the theory of probabilities is at bottom only common sense reduced to calculus. It makes us appreciate with exactitude that which exact mind feels by a sort of instinct without being able to oft times to give a reason for it. The idea is that that's kind of an interesting idea, right? Probability is just common sense reduced to calculus. And now there's other places we've used common sense rules when that common sense fails us, right? So the principle of indifference, treating things as equally likely, is a common sense rule that mathematicians, statisticians, lots of people fall back on. When we run our Bayesian models and we assume uniform priors, we fall back on that principle. I would argue another rule we can fall back on is this risk-reward rule. And in this case, what I hope to have shown you is that the risk-reward rule makes not just good common sense, but good ecological sense. With that, I want to make sure I thank Ralph. Many of the people are in here. Ralph, Larissa Conrad, who's not here, which I did with we did this work with the behavioral ecology. Christina Leuker, her fingerprints are everywhere in this presentation. She's the doctoral student. Torsten Pakur, Christine Schulze is also here with the learning from others, and then Lazare, who is a research assistant now in ARC, who also helped with the repugnance aspect. And with that, I'll stop and open up for questions.